Okay, class, this is aromatic reactions part 2. For an overview, we're going to first talk about the nucleophilic aromatic substitution, also referred to as the SNAR reaction. Okay, so this has an addition elimination sequence, and we'll talk about some of the adductive effects that are necessary of substituents to help in product formation. All right. The next class of nucleophilic aromatic substitutions are going to undergo a benzyne intermediate, and this sequence is an elimination addition mechanism. All right, and we'll talk about some unique things there. All right. Next, we move into our last class of nucleophilic aromatic substitutions, which is the semi reactions. All right. So if we take any type of aroamine, we like to classify these as anilines. We can do this diazotization reaction that will convert the NH2 of the amine into an N2. And then from the N2, we can introduce different nucleophiles to add on an OH, a Cl, Br, Cn, I, etc. Okay. We'll talk about some contemporary chemistry, the palladium catalyzed arrow substitutions. There's three main reactions: the Heck, the Suzuki, and the Stille coupling reactions. We'll move into side chain reactions. This is moving away from aromatic chemistry, but whenever we add our different products, those side chains have potential, I guess, to react as well. And then we'll end with some arrow ring reductions and hydrogenation reactions. Okay, let's look at the nucleophilic aromatic substitution. If we take a look at p-chloronitrobenzene, and we introduce it to a nucleophile here, lithium hydroxide, I'm sorry. All right, this compound, chlorine, can be substituted, all right? So the first thing that is important is to recognize here that chlorine will be our substituting atom, and that's different from the electrophilic aromatic substitutions where typically an H was lost. All right, for the NES reactions, they're typically going to be a leaving group that's going to be substituted. Okay, in this case here, chlorine is a leaving group. All right, so uniquely, this mechanism is unique because we're going to go do an addition then elimination step to overall gain a substitution. So the first step is that the nucleophile is going to attack the carbon that has the chlorine. All right, instead of the chlorine breaking at this step here, the pi bond has to break. All right, the pi bond is weaker than the sigma bond. So it makes sense, I guess, chemically to break that pi bond. That's going to generate our sigma complex that has a negative charge on the neighboring carbon. In blue here, these are the other carbons that gain a negative charge through resonance. What's important here is the carbon that has a nitro group. There's a negative charge that builds there, and that's a very favorable process. Again, the nitro is electron withdrawing. So electrons builds there, they can be delocalized into the nitro group. That makes this a very favorable process. All right. So the trend typically here for nucleophilic aromatic substitution reactions, the aromatic ring needs to be electron poor. So the more electron withdrawing groups you add to the ring, the better. All right, because in the mechanisms you're going to gain a negative charge, and the best way to help compounds that gain negative charges are to have electron withdrawing groups that can kind of suck up some of that electron density. Okay, so this first step here again is the addition step where we make a bond to our nucleophile. So now we have a carbon OH bond and we gain this lone pair and negative charge on the neighboring carbon. All right, these electrons can go back and reform a pi bond while kicking off our chlorine. And this is favorable because now when we reform that pi bond, we have an aromatic system. All right, so that step is the elimination step, and we gain overall a new substituted product. Instead of having a chlorine on the ring, now we have an OH. So the two steps here again is the addition step, all right, and then we have the elimination step to get our final product. Let's take a look at a few examples really quickly. So if I give you this molecule that has two chloros, all right, one chlorine is para to the nitro and the other one is meta to the nitro group. Okay, if we take sodium hydroxide here, we only get substitution at the carbon that was para to the OH. And again, because of the way that the ring would gain the negative charges or the lone pairs, all right, it's preferred to have the negative charge build at the carbon that has a nitro. If we attack the carbon that was meta to the nitro, those carbons will never gain those charges. So that will be an exercise for you to try to confirm that you can see all the possible resonance structures that are gained from attacking the paranitro or the metal, I'm sorry, the parachloro or the metal chloro to the nitro group, all right, to confirm that attacking at the parachloro gives favorable resonance structures, and this makes that chlorine more reactive in the reaction. All right. If we look at the below structure again, we have a bromo that's ortho to two nitro groups, and then we have a bromo that's meta to two nitro groups. And I guess you guys know the trend here that being ortho is better. Again, that allows those two carbons that have the nitro groups to gain a negative charge, which is going to be an extremely stabilizing effect. And this affords one product where the bromo that was ortho to those two nitro groups were substituted with the NH2. So the take-home point here is that the aromatic ring again prefers to be extremely electron poor, and electron withdrawing groups that are ortho or para to our leaving group are going to be preferred to be substituted in NAS substitutions, or nucleophilic aromatic substitution reactions. Okay, so let's take a look at another reaction here. I just have bromobenzene here, and I have a strong base, all right, slash a nucleophile here, if you want to think about it that way, all right. So typically this compound does not have the electron withdrawing groups that we saw from the nucleophilic aromatic substitution, all right. So this bromo cannot be substituted the same way that we saw from those earlier reactions. Instead, we have a new mechanism type that is called the elimination addition sequence. All right. So first, our reagent acts as a base and is going to extract a proton. The corresponding electrons are going to form a new pi bond while kicking off our bromo, okay, or the bromine. So this elimination leads to this very unique compound that has a triple bond in the ring. And I know this goes against most of the rules or things that we taught among atoms that are attached to triple bonds. They're typically linear, all right? However, this compound is real, and it has very strained bonds here, all right? The strained system here makes this triple bond extremely reactive. So benzynes are extremely reactive, all right? So in this case here now, this is where we get the addition step, all right? So the amine here can attack either carbons of the triple bond equally. Doesn't matter which one here in this case, okay? So after we get this addition step, we're going to generate this amine that has a lone pair on the neighboring carbon, and that lone pair can be protonated by just liquid ammonia, and that's going to give us our aniline substrate, okay? So again, we're just learning a new mechanism type. Typically with these strong bases, you're going to end up generating these benzynes intermediates, two steps. First the elimination, followed by the addition. Okay, so let's take a look at our practice problem really quickly. Let's say I gave you this trifluoro or methyl orthochlorobenzene reagent that's reacting with sodium amide. Let's see what happens here. Okay, so potentially we know that this is going to form a benzyne. Okay, we're not set up to do the NES reaction. Okay, even though the trifluoromethyl group is a leaving group, is not as strong enough as a nitro would be. Okay, so I have two potential carbons that I can now do my addition step at, A and B. And if I look closely at these two structures, I start to see that structure B is more stable. It's stable because the lone pair that builds is closer to the trifluoromethyl group, right? Being closer to that group inductively helps with stabilizing the negative charge that builds. Okay, so this is the final product that you get, and uniquely this is the only product that is formed from this reaction. And this kind of fits the model of having a benzyne here. If not, you would think of just substituting at the carbon that has a chlorine, and we see here we don't get that product. Instead we get the nitro group on the neighboring carbon, and that's only present through the benzyne intermediate. Okay, so now let's learn the semi-reaction. And typically in these reactions, nitrogen gas will act as the leaving group. So first we want to figure out or learn how to form N2 on an arrow ring. First, people nitrate an arrow substrate to form NO2, and NO2 is reduced with tin and ACl into NH2. All right, NH2 can then be converted to N2 with a step that is called diazotization. Typically, nitric acid is used. All right, so HONO is typically how most people like to draw this. It's easier to see that you're going to form a molecule of water, and you're going to form N2 is going to be your acting electrophile. But nitrous acid can be written as HNO2, and some people write it as a mixture of sodium nitrate with ACl. Now that I have NO2 as my starting substrate, this can be introduced to a lot of different nucleophiles to generate a lot of different aero products. If it sees water or just warm water, or this copperous oxide, you're going to form phenols. All right, if it sees copper 1 chloride, you're going to have aerochlorides. Copper 1 bromide, aerobromides. Copper cyanide, you will have the cyanide in the ring. HbF4, you get these aerofluorides. Hypophosphoric acid, you'll generate back your aero compound with an H replacing the NH2. And if I have another aromatic compound, you can start to generate these azo dyes. Okay, so now let's take a look at the contemporary arrow substitutions, and typically these are palladium catalyzed reactions. Just for review, nucleophiles do not react at arrow halides as well as vinyl halides. They do not undergo the SN1 or SN2 reactions. All right, so you want to kind of keep that in the back of your mind. However, organocuprates are a clever strategy around that. They will react with arrow and vinyl halides. So cuprates are a nice way to convert that halide into some type of R group. And conveniently, even more, accessible are the palladium catalyzed reactions. Again, these are using a small amount of palladium that gets regenerated in the reaction. So this is a very nice strategy as well to kind of react arrow halides. If I take palladium 0 with vinyl or arrow substrates, this is known as the Heck reaction. Okay, if I take palladium 0 and react it with these boron type of arrow compounds, arrow esters or boron vinyl substrates. Okay, this is known as a Suzuki reaction. And if I take these 10 arrow complexes or vinyl complexes, this is known as Stille coupling or the Stille reaction. Okay, and typically they'll just allow 2 arrow rings to come together and replace that bromo or the bromine, or have 2 arrow and a vinyl group to come together. All right, with the Heck reaction, however, there's a little bit of extra tricks or some concerns to keep in mind. Both ends of the vinyl group or all potential carbons on the arrow ring can react, so that can make Heck a little tricky to run. However, for Suzuki and for Stille, only the carbon that's bonded to the boron or to the tin are going to be the reacting carbons in those reactions. Okay, let's look at reactions to arrow rings. The Birch reduction is a single electron reduction. It would take benzene and reduce it to 1,4-cyclohexadiene. And to do the Birch reduction, I need either sodium metal or lithium metal dissolved in liquid ammonia. Substituents can be present. And if I look at this substrate here, if I take the methoxy or the anosol and do a Birch reduction, all right, I generate a vinyl ether that can be hydrolyzed into a ketone. All right, and those substrates, these conjugated ketones, are high value substrates. All right, so the Brooks reduction is a very convenient way to generate these type of compounds. All right, another reaction to arrow rings is this catalytic hydrogenation. All right, so under high pressures, this is high pressures of hydrogen gas over our metal catalyst, that could be palladium, platinum, or nickel. I can take benzene all the way down to cyclohexane. All right, let's consider our last topic in aromatic reactions, and these are reactions to side chains. The first is halogenation. If I have a aryl substrate that has an alkyl group that contains hydrogens, those hydrogens on that alkyl group can be replaced with a halogen. In NBS, our benzobrominating reagent is a good example of a side chain reaction. All right, next is oxidations. If I take this toluene substrate and introduce it to potassium permanganate, it will oxidize that carbon to a carboxylic acid. Okay, so what's important in the halogenation and oxidation steps is that the carbon or that alkyl chain has to have hydrogens. If it doesn't, it will not substitute for an halogen, or it will not oxidize up to a carboxylic acid. Okay, substituents can also be reduced. All right, and we can take these ketones all the way back down to the halogens with the Clemmensen or the Wolff-Kishner reductions. All right, and the only difference between the two is that in the Clemmensen reduction, these are acidic conditions. In the Wolff-Kishner, as basic conditions. All right, Clemmensen reduction, you need zinc that's treated with mercury with ACl at reflux, and for the Wolff-Kishner, you need hydrazine with potassium hydroxide and water. All right, and again, the carbonyl is replaced with two H's, so this is a convenient way to take ketones, aldehydes, all the way back down to the alkyl chains. All right. All right, just a reminder, with alkyl halides, all right, don't forget that they can be substituted with different nucleophiles. They can be eliminated with bases, or they can be converted into organic metallic reagents. All right, so forming these alkyl halides just releases all the previous chemistry that you guys have learned in organic chemistry. Okay, here's a free practice problems. Can you propose a synthesis of this compound from benzene? Okay, here's my answer. Can you synthesize metachlorobenzoic acid from toluene? If needed, please pause. Okay, two more examples. Can you provide the final product from these reactions? If needed, please pause. All right, here's the answers. Please, if needed, schedule office hours with me. We can talk about these answers. Good luck studying.